Now we will discuss the different modes of operation of a p-n junction. We already talked about a p-n junction under thermal equilibrium, which means the applied voltage is equal to 0. As you can see over here, we got two terminals. One terminal is connected to the p junction and another terminal is connected to the n junction. But it's open circuited, which means we have not applied with any voltage to the p-n junction. And in that case, we got a depletion width because of separation of the positive and negative charges. And then we got an energy band diagram with a built-in potential barrier for carriers to flow from one side of the junction to the other side. Another mode of operation is reverse bias. When the voltage is less than 0, that means we apply the negative potential to the p-type semiconductor and similarly the positive potential to the n-type semiconductor. By doing that, what happens is the positive potential is connected to the n-type semiconductor, so this positive potential would attract electrons from the depletion region, and the negative potential would attract holes from the edge of the depletion region. So because of that, the edge of the depletion region now widens. Compare this depletion width with the depletion width under thermal equilibrium. So now you see that the depletion width has increased. And also look at the energy band diagram. So let me tell you one key property for the p-n junctions, and you got to remember that. Regarding the energy band diagram, the side on which a potential is applied would be dragged down. For example, over here we apply positive potential to the n side. So this side of the energy band diagram would be dragged down. This side is dragged down. So now the potential across the p-n junction has increased. It's equal to the built-in potential plus the applied reverse bias voltage. The third mode of operation of a p-n junction is operation under forward bias, which means applying positive potential to the p-type semiconductor and a negative potential to the n-type semiconductor. When you apply positive potential to the p-type semiconductor, it pushes holes into the depletion region, and similarly the negative potential pushes electrons into the depletion region. So the effective width of the depletion region would be smaller as compared to the depletion width under thermal equilibrium. So in that case, as you can see, the built-in potential barrier has also decreased. The built-in potential barrier is now the difference between the potential is now the difference between the built-in potential and the applied voltage. And similarly, once again, as I already told you that in case of for the case of energy band diagram, the side on which positive potential is applied would be dragged down. For example, here we apply positive potential to the p side. So this side of the energy band diagram would be dragged down under forward bias. As you can see, this side is dragged down, and the potential across this barrier has decreased. Under the application of reverse bias, now the Fermi level is no longer constant throughout the entire semiconductor material. I told you that for thermal equilibrium, we will have a constant Fermi level throughout the entire semiconductor. But under reverse bias or under forward bias, the Fermi level would not be constant. For example, over here, now we have got two values for the Fermi potential. The Fermi potential on the p side and the Fermi potential on the n side of the semiconductor. So now the total potential V total is equal to the sum of phi Fn plus phi Fp plus the applied reverse bias voltage. And similarly, for different kind of calculations, you have to cater for the reverse bias applied potential as well. For example, here is the formula for calculating the depletion width. Now it's the same as it's similar to that of the depletion width for thermal equilibrium, but now we have an additional parameter over here, VBI plus VR. And with just the inclusion of VR, now we have an equation for calculating depletion width for reverse bias case as well. Consider an example. It's similar to the previous one. We have acceptor doping, the donor doping, the intrinsic carrier concentration is known for silicon, and now we are asked to calculate the depletion width under the application of 5 volts reverse bias voltage. So using the equation given in the previous slide, replace all the values. 5 over here is the reverse bias voltage, and putting in all the values, now the depletion width comes out to be 2.83 micrometers. So compare this with the depletion width for the previous example under thermal equilibrium. We saw over here under thermal equilibrium, under the same conditions, the depletion width comes out to be 0.951, while under reverse bias this has increased to 2.83 micrometers. So here is the proof that when you apply reverse bias voltage to the PN junction, its depletion width would increase. The electric field under reverse bias. Here are the equations for calculating the maximum electric field, which would happen at the metallurgical junction. And here, if you replace Xn with its value and also cater for the reverse bias voltage as well, include VR in this equation, you got equations for calculating the maximum electric field. And you can also represent it in terms of W. So here are 3 different equations with the help of which you can calculate the maximum electric field. Consider a PN junction, silicon at room temperature, the acceptor doping is given, and we are asked to determine the n-type doping concentration such that the maximum electric field is given at a reverse bias voltage of 25 volts. Now in this case we are going to use this equation, and the reverse bias voltage is 25 volts, and generally the built-in potential is, what is the range of the built-in potential? Do you remember it? I told you the built-in potential would be in the range of 0.5 to 0.9 volts for silicon. Roughly you can say assume it to be 0.7 on the average. So the built-in potential, we don't know the value of built-in potential, and in order to calculate that we need both acceptor and donor doping, but donor doping is not given. But the built-in potential is much lower as compared to, it's going to be in the range of 0.5 to 0.9 volts. It's going to be much lower as compared to VR, which is 25. So we just say as compared to VR, VBI is just a smaller number. So we are going to eliminate this from the equation. And Emax would be approximately, the magnitude of Emax would be approximately 2E VR divided by epsilon S in A and D divided by NA plus ND. The maximum electric field is given. All the other parameters are given, but ND is missing. So rearrange the equation for ND and we get its value using this equation. For a PN junction, we have separation of positive and negative charges. And whenever there is a separation of positive and negative charges, it means there would be a capacitance in that region as well. Capacitance is equal to Q divided by V. Q is equal to CV as a basic equation, as you already know. Or with increase or decrease in the reverse bias voltage, this depletion width would also increase or decrease, and the charges in the depletion region would also increase or decrease. So we can also represent C in terms of the derivative charge over the voltage. And then dq dash, we got different equations for it, but I'm going to jump to the final result. Here is the equation for the calculation of the junction capacitance. All these parameters we already know about the description of them, and we can also write it down in this simplest form. C dash, or the junction capacitance, is equal to permittivity of the semiconductor divided by the width of the depletion region. By the way, the unit of junction capacitance is farad per centimeter square. So if you want to convert it into farads, you need to know the area of the cross-sectional area of the p-n junction. Calculate the junction capacitance of a p-n junction. Consider the p-n junction in example 7.3 with a VR of 5 volts. So here is example 7.3, I guess, is this equation. We already know W, which is the junction, which is the depletion width under reverse bias of 5 volts. Reverse bias of 5 volts, put in all the values, and now the junction capacitance is equal to 3.66 into 10 to the power of minus 9 farad per centimeter square. Assume the cross-sectional area is also given. For example, A is equal to 10 to the power of minus 4 centimeter square. So the total capacitance would be C dash, which is farad per centimeter square, multiplied by the cross-section area of the p-n junction. So you get the total junction capacitance in farads. Generally, the value of junction capacitance is in picofarads. So if I give you an example, and if your value is too high, you need to double check your calculation, because you should expect the junction capacitance in picofarads. Now consider the case in which we got a one-sided junctions. Like for example, consider a P plus N junction. A P plus N junction means that the N-type region is lightly doped and the P-type region is heavily doped. And here is an equation for calculating the depletion width of a P-N junction. So in this equation, since it's a P plus junction, the acceptor doping is much higher as compared to the donor doping. So we can say NA is much greater than ND, so we can just replace it with NA divided by NA, ND. NA and NA cancel out. So we got this form. For a one-sided P plus N junction, the total depletion width is inversely proportional to the donor doping concentration, or the doping concentration of the lightly doped material, which also means that for a one-sided junction, most of the depletion width would be accommodated in the lightly doped material. For example, here the lightly doped material is ND. So Xn will have a much higher value as compared to Xp over here. And you can also see it like here is a P plus N junction. You can compare the size of the depletion width on the P side to the size on the N side. So most of the depletion width would be accommodated in the lightly doped semiconductor for a one-sided junction. Let's go back to the junction capacitance, and let us try to find an equation for one-sided p-n junctions. So C dash is equal to epsilon S divided by W, a simple equation. We already derived it in one of the previous slides. But for a one-sided junction, for example, for P plus N junction, we say that the depletion width is inversely proportional to the doping concentration of the lightly doped material, which for a P plus N junction would be the N-type semiconductor. So replace the value of W in this equation, and you got an equation for C dash. Take the reciprocal of this equation and then square both sides. So we get 1 over C dash square is equal to 2 times VBI plus VR divided by charge on electron, permittivity of semiconductor times the donor doping. And it's an equation. It's it's analogous to y is equal to mx, where m represents the slope. So we have an independent variable which is 1 over C dash square on the y-axis. We have a dependent variable 1 over C dash square y on the y-axis. We have an independent variable which is VR, and we have a slope. The slope can be represented by 2 divided by charge on electrons times permittivity times the donor doping. So this is actually an experimental method in order to calculate the doping concentration for one-sided p-n junctions. You apply reverse bias voltages, change the reverse bias voltages, calculate 1 over C dash square, and then plot them. You get a slope, and just equate the slope to this value, and from here you can calculate the donor doping concentration. It's an experimental method, a really useful method for material scientists and for engineers to calculate the doping concentration of the lightly doped material in a p-n junction. Here is an example for a one-sided junction. We have to determine the impurity concentration in a p plus n junction given the parameters from figure 7.11. This is figure 7.11. Assume that the intercept and the slope of the curve are VBI is equal to 0.725. The intercept over here VBI is 0.725, and the slope is 6.15 into 10 to the power of 15 farad per centimeter square minus 2 to the power of minus 2 times V to the power of minus 1. This is the unit of the slope for a P plus N junction at T is equal to 300 Kelvin. So here is the equation for the slope. Just replace the value of slope and reorder this equation. You can calculate the value of ND. ND is equal to 2 divided by ES times 1 over the slope. So the donor doping concentration in this case is 1.96 10 to the power of 15 per centimeter cube. From the expression for VBI, which is VBI is equal to VT, so here is the equation for VBI. Now we know the doping concentration of the lightly doped material for the P plus N junction. But how about the doping concentration of the heavily doped material, which is the p-type semiconductor? To calculate that, we already know VBI, which is 0.725. We have calculated ND. In this equation, we already know Ni is a material parameter for silicon. Reorder this equation, and we can calculate the value of Na as well for this P plus N semiconductor. Now, I want to introduce some basic concepts related to avalanche breakdown and Zener breakdown. Before jumping into the details of the breakdown voltage for different kind of diodes, let us first have a quick overview of the p-n junctions once again. For an unbiased p-n junction under thermal equilibrium, we have a depletion width, and it's going to have a certain potential barrier. Under forward bias, the depletion width narrows down, reducing the resistance of the depletion of the p-n junction, and it's going to have a certain built-in potential. Above that built-in potential, when we further increase the voltage, the current would drastically increase as well. Under reverse bias, the depletion width would increase, which would also increase the resistance of the p-n junction. So ideally, under reverse bias, the current would be 0, but there is a limit to the voltage that we can apply in reverse bias to this p-n junction. If we apply a too high voltage under reverse bias, there comes a point above which the current will start drastically increasing once again, and this voltage is called the breakdown voltage. By the way, the scale over here is not the same. Like for example, over here it might be 1 volt, but here it might be like 5 or 6 volts for the breakdown. So when the breakdown occurs, the device is damaged permanently. You cannot use it anymore. Now, there are two mechanisms responsible for breakdown predominantly. One is called avalanche breakdown, and the second one is called Zener breakdown. Avalanche breakdown occurs in lightly doped materials under the application of high voltages or under high electric field. So what happens that if you apply high reverse bias voltage to lightly doped material, or there is going to be high electric field, the electrons would gain enough kinetic energy so that they can knock off secondary bound electrons from atoms, and then these secondary bound electrons can further knock off more number of electrons from other atoms as well, starting a chain of reactions resulting in an avalanche or a multiplication factor. So we have a lot of carriers now available inside the semiconductor under reverse bias, and because of that, a high current would flow under reverse bias, damaging the p-n junction. Another breakdown mechanism is Zener breakdown, and it occurs in heavily doped material. Heavily doped materials are represented by the plus sign, P plus and N plus. For heavily doped material, we got a narrow depletion region, and also its energy band diagram is represented over here. So for heavily doped materials, the energy band diagram is rearranged in such a way that now the conduction band, the electrons in the conduction band over here are directly aligned with the electrons below the valence band on the p type of the semiconductor region. So now electrons, which means that we have a narrow region, and electrons can easily flow from this region to the right above the conduction band on the n-type region. And because of that, large current can flow even under the application of reverse bias voltage, resulting in permanent damage to the device structure. And this is called breakdown. One key phenomenon once again to understand is that here we are applying the positive potential to the n-type of the inside of the semiconductor or the p-n junction. So whenever we apply positive potential to this side, it's going to be dragged down. Temperature coefficient is a little bit advanced phenomena. I've personally worked on it at Georgia Tech in my PhD study. Zener diodes have a negative temperature coefficient, which means that with increase in temperature, the breakdown voltage also would decrease. But avalanche diodes have a positive temperature coefficient, which means that with increase in temperature, the breakdown voltage would increase. Anyhow, this is an advanced phenomena, so I don't want to dig deeper into this concept. But moving on to the next slides. Here is a comparison of Zener breakdown versus avalanche breakdown. Zener breakdown occurs in heavily doped materials, and its value is roughly, like for silicon, it's below 4 volts. But avalanche breakdown occurs in lightly doped materials, and for silicon, its value is above approximately 6 volts. Here is a comparison of avalanche versus Zener breakdown. We already talked about these points, so I'm going to skip this slide. Here is another important slide. Breakdown for a one-sided P plus N junction. So we already covered the formula for maximum electric field, which is equal to E times Nd Xn divided by permittivity of the semiconductor. And then for a P plus N junction, the depletion width is approximately equal to the depletion width on the inside of the semiconductor of the lightly doped material. So here is an equation for Xn. Replace Xn into the maximum electric fields equation, rearrange this, and here VR is the reverse bias voltage. Emax is the maximum electric field or the critical electric field at which the breakdown occurs. So replace reverse VR with VB, the breakdown voltage, because it's a reverse bias voltage and at this voltage the breakdown occurs. So replace VR with VB and replace Emax with E critical. It's the critical voltage, the voltage at which the breakdown occurs, the peak electric field. And replace ND with NB. Like here we are considering P plus N junction, but NB means the background doping concentration of the lightly doped material. So here is an equation for calculating the breakdown voltage for a one-sided junction. And also there are plots, so you can look at the plots, and from the plots you can determine the breakdown electric field as well. For example, the blue curve over here represents silicon material, and this curve over here represents a one-sided abrupt junction. So we are mostly going to focus on abrupt junctions. And on the x-axis we have impurity concentration of the lightly doped material, Nb, and on the y-axis we have the breakdown voltage. Similarly, there is another plot for critical electric field versus the background doping concentration of the lightly doped material as well. Now let us focus on this example. Design an ideal one-sided N plus P junction. Now in this case, the P-type material is the lightly doped material. To meet a breakdown voltage specification, consider silicon at room temperature. The donor doping is given. Design the diode such that the breakdown voltage is 100 volts. So in this case, we know the breakdown voltage and we know the donor concentration, but we have to calculate the acceptor concentration. The donor concentration is given. It's the N type is the heavily doped side for the one-sided junction. We have to calculate the acceptor doping, the lightly doped, the carrier concentration of the lightly doped material. So the breakdown voltage is given. We can determine it with the help of the figure given in the previous slide. So the breakdown voltage is 100 for silicon, and this blue curve, this curve over here represents silicon. So for this 100 volts, try to find the corresponding point on the blue curve. This is the point which intersects the blue point for a breakdown voltage of 100 volts. And at this point, the impurity concentration is approximately 1, 2, 3, 4. 4 into 10 to the power of 15 per centimeter cube. So the impurity concentration of the lightly doped material is 4 10 to the power of 15 per centimeter cube. So we determined from the plot that the impurity concentration is 4 10 to the power of 15 per centimeter cube for a breakdown voltage of 100 volts. Similarly, going back to the slides, for the same impurity concentration 4 10 to the power of 15, the critical electric field, or the electric field at which the breakdown occurs, is approximately 3 into 10 to the power of 5 volt per centimeter. So 3.7 in fact. 3.7 10 to the power of 5 volt per centimeter is the breakdown field. And we calculated these values from the figure. Now to cross check, you can also use this equation, right? We got the critical electric field over here and the background doping concentration over here. Replace the values. The breakdown voltage is approximately 110 volts, which is close to the value of 100 volts. So you can determine these parameters, the breakdown voltage, critical electric field, and the doping of the lightly doped material either from the plots, this plot over here and this plot over here, or by using this equation. So this concludes the topics for today. We still got to cover more number of topics for the p-n junction diode, but there are a lot of parameters. For example, the intrinsic carrier concentration of silicon, the intrinsic carrier concentration of gallium arsenide, charge on electron, permittivity of semiconductor, permittivity of silicon, permittivity of free space, permittivity, relative permittivity for silicon, relative permittivity for gallium arsenide, relative permittivity for gallium nitride, for other materials. There are a lot of parameters that you need to get familiarized with, and the only way to get familiar with these parameters and with the mathematics and with the physics and equations is to solve problems. So here is your assignment number 1. You got to solve problems 7.1 to 7.11, 7.16 to 7.26, and 7.35 to 7.40 from Semiconductor Physics and Devices by Donald Neiman, 4th edition. I'm going to share the book with you in the group chat. And this assignment is due by the next lecture, so you got to submit it before the lecture on next Wednesday. And I know it's a little bit extensive assignment. With the passage of time, I'm going to reduce the size of the assignment, but at this point you need to practice a lot so that you are able to understand the future concepts for diodes, and then for Schottky diodes, and then for LEDs, solar cells, photodetectors. So that concludes the lecture for today. Do you have any queries for me? Well, if not, that's it.
Sir, kindly lecture के material share कर दीजिएगा.
Yeah, sure. I'm going to share the lecture slides for today, and also the previous lecture slides with you, and also the book chapter on the group chat. Sure, I will do that. And I will have the recordings, but the recordings are like they're like, each video of them is like 700 800 MBs. So either you can copy it from my computer, or I'm going to upload them on the Google Classroom whenever the classroom is available. Right? Take care. That's it for today, and I will see you next time, inshallah. Allah Hafiz.